your introduction, Chitalia. Hello, everyone. Thank you for being here. I'm very excited to share with you today the research that my group and I have been working on. I will be telling you about how we can decode hidden worlds using signals in our oceans, bodies, and beyond. As humans, we crave to explore hidden worlds. This curiosity has driven us to pursue journeys to explore our environment, our seas, our oceans, and go even beyond our planet to explore outer space. We're also curious to explore the hidden worlds inside our bodies, to learn about our health and our own selves. And yet, we still know so little. Let us take our oceans. As of 2018, more than 20% of the ocean remains unobserved and unexplored. 80%. Even our human bodies, at any point in time, I know so little about what is going on inside my body. Am I recovering? Am I getting sick? Do I have coronavirus? I don't know. And it's quite difficult for me to get that information right away. And even when we try to build machines that allow us to explore the world and interact with it in new ways, many of the world remains hidden from these machines. For example, even when we build our best robots, we want to make them see things just like us humans. But what if we could make them see things that are invisible to the human eye? These questions have driven my group and I to think about how we can develop technologies that would allow us to explore and decode hidden worlds in our oceans, inside our bodies, and through our robots. At the heart of all of these technologies are signals that we use to perceive, sense, communicate, and decode. And in this talk, I will be telling you about these technologies, about sensor technologies to decode hidden worlds. I will tell you first how we design and build these sensors from the materials and hardware all the way to the algorithms and learning models. So sensors, hardware, and learning. I will tell you how we use these signals, how these sensors use signals in order to power up, sense, and communicate. And I will also tell you how these sensors can decode new worlds and hidden worlds underwater, in body, and through robotics. And how by decoding these worlds, they can help us address major problems in climate, healthcare, and automation. And the way I'm going to do this is by dividing these technologies into their domains. First, I will tell you about oceans, then about the human body, and finally, about robotics and automation. Now, I will spend most of my talk telling you about oceans, then I will briefly tell you about our work in the human body, and finally, touch on some of our work in robotics. So let us start with oceans. Remember that what I said earlier, more than 80% of the ocean remains unobserved and unexplored. And so what we wanted to do is we wanted to build and deploy an Internet of Things for the ocean that can allow us to explore and observe this hidden world. So this can be used for ocean exploration. It can be used for underwater climate monitoring, for example, taking images of coral reefs. And it can also help in emerging industries like aquaculture, which is supposed to support many of the world's growing food demand over the next few decades. And as we started looking into these applications and trying to deploy an ocean Internet of Things, we ran into a major problem. The problem was that the battery life of underwater sensors is extremely limited. As we look deeper into this problem, we realized that the reason is that underwater transmissions consume lots of power, hundreds of watts. And this includes the most recent low-power micromodem from the Woods Hole Oceanographic Institute. And as a result, state-of-the-art sensors for tracking marine animals can only last for a few hours or days, after which their battery dies out. This makes it very difficult to use these sensors for long-term climate sensing or for discovering migration patterns of marine animals. And this got us thinking about ways to reduce the energy consumption of underwater communication. So today, I will be telling you how we could overcome this challenge by developing the first technology that enables underwater backscatter networking, or batteryless networking. This kind of communication technology consumes near zero power, which allows our sensors to operate over a very long period of time without requiring any batteries. Let me describe to you how this technology works at a high level by comparing it to how traditional sensors communicate underwater. In these environments, you typically have an underwater drone or a submarine or ship that communicates with various sensors. So let us just focus on one sensor. For those of you who are not familiar, underwater you cannot use standard IoT technologies like Wi-Fi or Bluetooth because they do not work there. To send information to the drone, today's sensors have to use acoustic signals like sound or sonar. So the sensor has a speaker, and the receiving drone has a hydrophone or underwater microphone, and the sensor sends sound waves. The problem with this approach is that generating acoustic signals requires a lot of energy, which drains the sensor's battery. In contrast, our technology does not require the sensor to generate any acoustic signal. Let me tell you how it works. In our design, the speaker and the hydrophone are both at the drone, and the sensor is connected to an acoustic reflector, which you can think of as a mirror. So when the transmitter sends sound, it reaches the sensor, then reflects back to the receiver. Now, in order to communicate information, all the sensor needs to do is to toggle its reflector between reflective and non-reflective states. Once it can switch between two states, it can communicate bits of zeros and ones and send its sensor data. So to summarize, in traditional communication, a sensor must transmit its own acoustic signal, which is power consuming, while in our technology, it just needs to turn a switch on and off, and it can communicate by reflecting existing signals. And because the drone is in a privileged location and it has its own power source, what this allows us to do is to shift all the power consumption from the sensor to the drone itself and make the sensor battery free. So this is all great, but there's still one main question, which is, how can we control the reflections of acoustic signals? Our idea is to use piezoelectricity to design programmable acoustic reflectors. Piezoelectric materials transform mechanical to electrical energy. Let me explain this using a simplified example. Let us say you have a piezoelectric material and try to measure the voltage across it. If you have a speaker that transmits acoustic signal, the signal travels as a pressure wave and causes the piezoelectric material to vibrate. This vibration creates an electric signal across the terminals of the piezoelectric material. So effectively, the material has transformed mechanical energy, which is sound, to electrical energy, which is voltage. But remember, what I want to do is to transform this material into a reflector. So to do this, I will simply connect this material to a switch. When the switch is open, the material behaves naturally and transforms acoustic signals to electric signals. Now let us see what happens when the switch is closed. When the switch is closed, it means that the two terminals of the piezoelectric are connected to each other. When the terminals are connected, you cannot have any voltage, so the device cannot vibrate. So now, when you transmit an acoustic signal, where does the energy go? It has to be reflected back. So by closing the switch, we are able to transform the piezoelectric material to a reflector. And now to communicate, all we need to do is to switch between reflective and non-reflective states. And this can be done using a simple transistor. And so the sensor can communicate without generating the power-consuming sound signal. We call this technology piezoacoustic backscatter because it uses the piezoelectric effect in order to communicate by reflection or backscatter. And as I will show you, our sensor needs 1,000,000 times less power, about hundreds of microwatts, rather than standard underwater acoustic communication. Not only this, our sensor also harvests energy in the non-reflective or absorptive states, which allows us to make it completely battery-free. So let me show you a video demonstrating our technology in action. This clip was shot in a large experimental pool, At the far end of the pool, you can see a hydrophone and our projector or speaker. And here's our sensor connected to a circuit that has an LED. Now let me play the video. Notice how the LED lights up. Remember that our sensor has no battery. So it lights up entirely based on the energy that it harvests. This is the energy that comes from the remote projector. And what this shows is that we can power up the sensor remotely. Now let us see if we can decode the sensor's response. So we use the hydrophone to measure the received signal. And let me show you what we got. Over here, I plot the amplitude, the normalized amplitude on the y-axis as a function of time on the x-axis. And this is the signal that is received by the hydrophone. At about 2.5 seconds, the speaker starts transmitting, which is why you see it jump in the amplitude. Then at around 3 seconds, the node starts backscattering. As you can see, the amplitude switches between two levels, which correspond to the two reflective states. This is because the hydrophone can sense the amplitude changes, it can use them to decode the backscatter packets. And if you're wondering, why doesn't the amplitude go all the way to 0 when it is absorbing or not reflecting? Remember that the hydrophone is not just getting the signal that comes from the backscatter node, but it's also getting the signal from the projector, which remains there. And it is never 0. So we went ahead and we built this technology, and in our implementation, over here you can see our batteryless sensor. We fabricated our own transducer. This is an exploded view of it. At the heart of the transducer is a piezoceramic cylinder, and we 3D printed end caps, added a bolt, encapsulated in polyurethane. We also built our hardware, which you can see here. Our hardware is able to harvest energy. It has an energy harvester and a microcontroller, among other devices. And if you're interested in building this yourself, we've open sourced the code and schematic to allow other researchers across electrical engineering, computer science, material science, and oceanographers to be able to build on this, even if they do not have the full stack expertise. We fabricated our projector in-house, and we bought a hydrophone. And in our evaluation, the projector sends a signal on the downlink, which the sensor can decode. So it can communicate on the downlink, and then it backscatter in order to communicate on the uplink. Now, one question that I usually get here is, how can you communicate without knowing where the reflector is? And the one thing that I want to say here is that the sensor, while I give the mirror analogy, it actually is able to get energy from all directions, and it is able to communicate in all directions. So the reflection is actually omnidirectional. So I want to show you quickly two main results from this technology. The first one is power consumption. Remember that the main benefit of our approach is that it reduces the power consumption. So we measured the power consumption of our prototype using a source meter in a setup like the one you see here. And here's a graph that plots the power consumption in microwatts as a function of bit rate. When the sensor is in idle mode, the power consumption is about 120 microwatts. And even when it starts backscattering, the power consumption jumps to about 500 microwatts. Of course, it makes sense that it consumes higher power when backscattering. But the key take-home message here is that the sensor communicates using 1 million times less power than state-of-the-art underwater modems. Next, what I want to show you is our power-up range. So we ran an experiment where we varied the power of the projector, and we measured the distance at which we were able to power up the sensor. We did our experiments in 2 different pools with different dimensions. And over here, I plot the maximum distance as a function of the transmit voltage. You can see that as the voltage of the transmitter increases, we're able to power up the sensor at further distances. Now, one thing that we realized is that the slope is different across different pools, meaning in one pool, it was easier to power up at a longer range than in the second pool. And the reason is because the pools have different dimensions, so the wireless medium is a bit different. But the most important thing to note here is that in both scenarios, we're able to power up the sensor from one edge of the pool to the other. And we're able to achieve a throughput of about 1 to 3 or 1 to 2 kilobits per second and a power up range at 10 meters. So we introduced this technology last year, and we are very excited by it. But it was still limited in order to allow us to achieve the big vision that we were after. The throughput is limited, so you cannot send high-resolution images, which you would need for example, monitoring coral reefs. And the transmit power range is limited. So then we started thinking about how we can increase the throughput, range, and scale of underwater backscatter while keeping it battery-free. Now, the problem that we were facing is that the resonance of piezoelectrics limits their bandwidth. Remember that our batteryless node relies on piezoelectric materials, and the way it communicates is by modulating its vibration. So the vibration controls the reflection. The problem, however, is that vibration happens at the resonance frequency. So for those of you who are not familiar, resonance is a natural frequency that a material vibrates out. So for example, if you were to take a guitar, and if you were to plug one of the strings of the guitar, you would hear a single tone. This tone is the natural frequency for that guitar string. If you were to choose another guitar string, you would hear another tone. And this tone is limited by the structure, by the mechanical structure of the guitar, or by the mechanical structure of the piezoelectric material. Now, the problem with this resonance is that it happens at a very narrow bandwidth. So if I were to plot the amplitude as a function of frequency for a piezoelectric material at 20 kilohertz, it will have a very narrow bandwidth. So the resonance leads to narrow bandwidth, and narrow bandwidth limits your throughput. So we started thinking about how can we overcome this resonance problem while maintaining the low cost and low power nature of underwater backscatter. So to do this year we introduced a novel metamaterial designs that enables ultra-wideband backscatter. Metamaterials are materials that do not naturally occur in nature. So now, instead of limiting ourselves to the natural frequency of a guitar string or the natural frequency of an existing piezoceramic material, what we did is we designed a new material that exhibits wide resonance. And what we've shown is that this new material allows us to boost the throughput, range, and scale. Now, I want to tell you at a very high level how we built it. Our key idea is that we created coupling between only two piezos in order to synthesize many different resonances. So what we did is that we took here two piezos, an outer one and an inner one. And then we got a soft polymer and we filled it between the two piezos, the outer and the inner one. And then we cooked it in a pressure chamber. So let me show you what this allows us to do. When we plot the amplitude as a function of frequency, because the polymer is soft, it's a rubber-like material, the outer and the inner piezo are still able to vibrate at their original frequencies. So you're able to get 20 kilohertz for the outer one, and 40 kilohertz for the inner one. But because we added the soft material that filled in the gap between the two piezos, what we also did is we created new constraints. And these new constraints result in new unnatural resonance modes. These unnatural resonance modes fill in the gap between the low and the high frequency. And by filling in these gaps, we're able to achieve a wide bandwidth. And so what this allowed us to do is that this metamaterial design enables us to overcome the resonance problem and achieve wideband operation. And now that you have wideband operation, you can achieve higher throughput, and you can bring in new tricks that exploit this wide bandwidth to allow you to communicate over a longer range. Then we took this technology and started testing it outside the lab. So we ran experimental evaluation in a river, in the Charles River in Boston, including in snow and rain, to try to test it in different weather conditions. We ran hundreds of experimental trials at different ranges, throughputs, and nodes. Over here, you can see one of experimental setups at the MIT Sailing Pavilion. And using this novel metamaterial, we're able to significantly improve the performance of underwater backscatter. We're able to achieve throughput of 20 kilobits per second. That's about 5 times increase over what we were able to get before. And this allows us to start transmitting low resolution images from underwater and being able to communicate them. It also boosted the range to 62 meters, again, by about 6 times, and allows us to scale this technology to 10 nodes concurrently. And this is even before spatial reuse. And now, our next step is to boost this throughput and range by even further and try to get a few orders of magnitude more, as we've been doing progressively, so that we can deploy this as a scalable ocean IoT. And I want to end my discussion of this technology by showing you a clip that we shot in the ocean. So over here, you can see 2 of my undergraduate students running experiment with the ocean. Here, what we did is we connected our sensor to a temperature and pressure sensor. This is important for monitoring ocean temperatures. For example, if you want to be able to monitor underwater climate change. We also experimented with pH sensors to monitor ocean acidification. And one of the exciting applications of our technology is even beyond our planet. NASA scientists recently discovered subsurface oceans in Saturn's moon Titan. So you can imagine using this technology in future space missions to look for and sample water in distant planets. So far, I've told you about this ultra low power ocean Internet of Things that allows us to communicate between submerged nodes. Another question that we wanted to ask is, how can we then send this sense information to the outside world? Not just keep it in the water, but be able to extract it. And as we started thinking about this problem, we ran into a new challenge. And the problem was that direct underwater to air communication is infeasible. So if you have a submerged sensor, it cannot directly transmit its information to a receiver above the surface. And this is true for underwater vehicles, and it is even difficult for submarines to communicate with airplanes without surfacing. And you might be wondering why. The reason is that wireless signals work well only in a single medium. For example, they work well only in air or only in water, but they cannot work well across both. For example, an underwater drone can communicate with the sensor using acoustic signals or sonar, as I showed you earlier in the talk. Cell phones and radio towers can communicate using radio signals like cellular or Wi-Fi. But neither of these works well in the other medium. A simple question one might ask is, why don't we just use acoustic signals to communicate with nodes in the air? Well, the reason is that if you were to send an acoustic signal to the water surface, it will reflect off, and so it will not be able to cross the boundary. So why not transmit radio signals? Well, this is because radio signals die in water, so they will not even reach the surface, which is why we use acoustic signals and not radio underwater in the first place. This is quite an old problem. So how do people overcome it today? Well, one approach to work around this problem is to use relay nodes. Let me tell you what I mean by this. You have a relay node that is partially submerged in water. It has an acoustic transceiver underwater and antenna in the air. So for example, if an underwater drone wants to communicate with the radio tower, it transmits an acoustic signal or sonar. The relay receives it, and then it retransmits it in the air as radio signals. That is how relays work. The problem, however, is that these relays can easily drift away with waves, which cuts the communication link. Not only that, you simply cannot furnish the entire ocean with relays in order to enable this type of communication. So another approach that people use today is that the underwater vehicle needs to surface to a depth at which it is able to effectively communicate using radio signals. But if you were to use this approach, it would take forever for this drone to keep going up and down, and it becomes very time-consuming and expensive process. So today, there's no effective way for compact underwater devices to communicate with others above the surface. And so to overcome this, my group introduced a technology that enables wireless communication across the air boundary. And what we've shown is that you can enable a compact underwater sensor to communicate with a compact airborne receiver. Here's our idea. We take an underwater speaker which transmits an acoustic signal. The signal travels as a pressure wave. When this wave hits the surface, it causes a very small vibration. Now, to pick up this vibration, we built a very sensitive radar. The radar transmits a radio signal, which reflects off the surface and comes back. And it gets this reflection and it uses it to measure the surface vibration. So now when the speaker transmits a different sound or different information, it causes a different vibration and the radar is able to pick it. And that is how we're able to communicate across the water-air boundary. Effectively, what we've done is transform the water surface from itself being an obstacle to being a communication interface. Now, one of the main, and we call this translational acoustic RF communication because it uses a translation from acoustic signals to radio signals to enable communication. And it allows us to achieve the best of both worlds, acoustic underwater and radio in the air. One of the main challenges that we face is that the ocean already has a lot of naturally occurring waves. And practically what's going to happen is that natural surface waves are going to mask the signal that is coming from underwater, these tiny vibrations at the surface. Indeed, even on calm days, ocean surface ripples, which are called capillary waves, have 2 centimeters peak-to-peak amplitude. And this is 1,000 times larger than the surface vibrations caused by the acoustic signals, which are only of the order of a few micrometers. So how could we sense this tiny vibrations despite ocean ripple? Our idea was to treat naturally occurring waves as structured interference and filtering them out. So let me tell you what I mean by this. Naturally occurring waves are relatively slow. They typically happen at a frequency of 1 to 2 hertz. But the acoustic signals that we're transmitting underwater are transmitted at a much higher frequency, at about 100 or more hertz. And so because they are separated from each other in the frequency domain, you can apply filtering mechanisms that allow you to eliminate the naturally occurring waves and decode the tiny vibrations that are being transmitted from underwater. And what we've shown is that we're able to deal with naturally occurring waves and communicate from underwater to the air. So in one of our earliest demonstrations, we experimented in a small tank that you see here. So we transmitted acoustic signals, and then we built a radar that is measuring the surface vibrations of at the surface. And we tried to communicate information and receive it. So for example, over here, we're able to decode a message, hello from underwater. We evaluated this technology in different places as well. We evaluated in a water tank. Over here, you can see the acoustic transmitter and the radar receiver. We also evaluated it in swimming pools, including in the presence of swimmers. And over here, we had circulation currents and swimmers that were causing surface vibrations. And you can see our acoustic transmitter and our radar receiver. And in all of these environments, we show that we are able to communicate from underwater to the air. Now, I want to show you briefly one result about how we can deal with waves. So we tried to artificially generate waves of different peak-to-peak amplitudes and measure the throughput. So on the x-axis, I plot the wave height, and on the y-axis, I plot the normalized throughput. Now, in the absence of wave, because I'm normalizing the throughput, I will divide by the maximum, and I will get 1. And this is the result that we get with 2 centimeters peak-to-peak. Now, this is a capillary wave. This corresponds to standard capillary waves in the ocean. And you see that we're still able to almost decode and get the entire throughput. Even if the wave height increases, we were able to communicate. But beyond 20 centimeters, we were not able to communicate as much information anymore. And that is because the wave height is so strong that it prevented us from being able to decode these signals from underwater. But the key message here is that this underwater to air communication technology is able to communicate in the presence of naturally occurring waves that are 1,000 times larger than acoustic vibrations, and in scenarios where state-of-the-art prior systems could not achieve any communication through. And we're now building on this technology, again, to also expand the range at which able to operate at, both in terms of depth and in terms of height, and test it in the real world, similar to how we've tested our ocean IoT. And with this, so far, I've told you about our research on developing technologies for decoding the underwater world and how we can extract this information. And next, I want to move on to a second part of my talk that decodes the human body. Now, as I mentioned, the rest of this talk, I will only briefly touch on the work in the human body and discuss on work on robotics. So don't worry, it's not going to be a 1.5 hour long seminar. So what we wanted to do in exploring the human body is that we wanted to build new sensors that we put inside the body and we use to decode information on the inside. Now, last year, a man received a chip, an implant under their skin at the World Mobile Conference. But the micro implant is very limited. It can only be implanted at superficial depths, and the only thing that you could do with it is identify the person. In fact, in a recent op-ed article in Popular Science, some who received the micro implant wrote, "My implant is both less scary and less useful than you might think." Now, while micro implants right under the skin are not very useful, if you can take them and put them deep inside the human body, they have enormous applications for digital medicine. So my group and I set out to take a microchip like this one, which has no batteries, and put it deep inside the human body. And we wanted to communicate with it from outside the body. So how can we power up and communicate with these microchips when they have no batteries? Our idea is to wirelessly power the micro implant. A device outside the body sends a wireless signal, which goes through the body, powers up the implant, and when the implant powers up, it is able to communicate information to outside the body. And this enables many applications in digital medicine. It allows us to decode the world inside the body. So for example, one of the major applications is in continuous sensing of biomarkers and tumors. You can imagine a network of miniature sensors inside the body, sensing conditions and sending information to the outside world. For example, they can continuously monitor a person's gut microbiome or stomach condition. In the future, this type of information can be able to predict diseases, enabling early intervention because you can monitor the body from the inside. Another application is in ultra-long-lasting drug delivery systems. Today, when a person swallows a pill, we expect the drug to be delivered immediately. But certain diseases like malaria need continuous drug delivery. And with such technology, you can control drug dosages over extended periods of time by sending commands to a smart pill that sits inside the stomach. People also don't need to remember to take their medications because you're able to trigger them over the course of the treatment. So this can also help patients who have Alzheimer's who might forget to take their medications. And there's many other applications for wireless and batteryless microimplants, including long-lasting artificial pancreas for diabetes patients and deep brain stimulators for treating patients with epilepsy and Parkinson's. So we can enable all of these applications if you can take microimplants and put them in deep tissues. The problem, however, is that existing batteryless microimplants can only work at very shallow depths. So to overcome this, my team developed a technology that can remotely power up and communicate with deep tissue batteryless microimplants. And the unique thing about our technology is that it can work from a distance outside the body. So you can imagine a sensor that sits at your bedside and is able to power up and communicate with another sensor that is deep inside your body. Now, the key challenge that we had to overcome is that wireless signals exponentially attenuate inside the human body. So if you were to transmit a wireless signal from outside the body, the signal decays 1,000 to 10,000 times faster inside the body than in air. This is why today's implants can be implanted right under the skin, and you cannot power them deep inside tissues if they do not have batteries. Now you might be wondering, why don't I simply transmit more power from the sensor that is outside the body? Well, there's two problems. First, the transmit power is limited by safety regulations and device properties. You don't want to blast an enormous amount of energy at the human body. And the second problem is that the micro-implant antenna itself, the properties of it change in different tissues, which makes it difficult to provide always-on availability. So we thought about how we can power and communicate with sensors in deep tissue despite attenuation and complexity that changes the properties of the microimplant inside the body. So to overcome this, we came up with two innovations. Let me tell you about them at a very high level. The first one is a beam focusing technology that is safe to the human body and that is able to deliver sufficient energy in deep tissues. So at a very high level, what we needed to do is to power up the sensor, we need to overcome a minimum threshold, minimum energy threshold that is dictated by the electronics. And so we structured the signals that we were transmitting in a way such that we're able to deliver this energy while remaining safe deep inside the human body. So that allows us to overcome the attenuation problem. The second problem was that depending on where the implant is in the human body, its properties changes. So how can we provide availability for one that is in the stomach versus if it is in the esophagus? And for that, what we introduce is a self-reconfiguring microimplant. This microimplant can change what it is by sensing its environment and adapting to it. So for example, if you were to take this flexible implant and laminate it on the stomach wall, then it can adapt to the stomach conditions. But if you want to roll it into a pill that gets swallowed and moves inside the human body, then it will sense and adapt to the surrounding conditions. Now, in the interest of time, I will not talk into more technical details about how we built these, but I want to show you one quick result about an evaluation that we did in a living animal. In collaboration with medical doctors and biomedical researchers at Harvard Medical School and Brigham and Women's Hospital, we tested our technologies in a pig, both right under the skin and deep inside the pig's stomach. And in both of these scenarios, we were able to successfully demonstrate wireless power and communication with batteryless microimplants in deep tissues inside living animals. And so looking ahead, this technology is very exciting because now it can open up so many applications. And so now we're building on it so that we can deliver new applications based on locating and nanosensing, stimulating, drug dosing, and monitoring. Another key research question that we've been looking at is how can we maintain the security and privacy of these sensors? Now that you're decoding the human body and opening it up to sensing from a distance, how can you make these sensors safe to both hacking, and how can you preserve the integrity of this information and its security and confidentiality as you're transmitting it to the outside world? And so with this, I've told you about our second focus, which is about decoding the human body from the inside and being able to gain more information. And finally, I want to touch on our work on enabling robots to decode hidden worlds. Over here, we're motivated by one main question, and that is, how can you enable robots to perceive things that are invisible to the human eye? For example, if I were to give a robot 2 boxes, can it know what is inside these boxes? In order for it to deliver more complex tasks than humans are able to do? If I were to give it a food or medicine bottle, can it know if it is safe or whether it is counterfeit? If I wanted the robot to fetch an item that it does not see in order to enable a task that is more complicated than what us humans can do, how can I enable the robot to fetch such an item? At the heart of our solution to all of these questions, in order to provide an affirmative answer to all of them, what we did is that we augmented the robots with wireless perception. At a high level, what we did is that we used radio frequency signals. RF signals like Wi-Fi can traverse walls, which is why you can get Wi-Fi even from another room. So if you were to augment a robot with radio frequency perception, then it can traverse occlusions. And what we've shown is that by augmenting it with this new perception module, we're able to extend the perception beyond the line of sight. So let me quickly show you a video of how the robot is able to grab an item of interest, even when it cannot see it. So over here, we have an item of interest that is tagged with an RF sensor. And the robot has a camera, but the line of sight of this camera is locked to the sensor. So the robot does not even know where to start looking for it. Should it start in the back? Should it start to the left? Should it start to the right? But because we have an RF perception module, it is able to locate it. And as you can see in the video, once it locates it, it is able to navigate towards it. And now when it navigates towards it, it can start seeing it with its camera, and then it can grasp it. So using the the wireless perception module, it was able to see through the occlusions in order for it to guide a grasping task that would have otherwise been infeasible using today's technologies. So I just wanted to give you a feel of the kind of work that we're doing in extending robotic perception beyond line of sight to decode hidden worlds. And so in this talk, I've told you about our sensor technologies for decoding hidden worlds in our ocean, the human body, robotics. Actually, my interest in decoding hidden worlds dates back to when I was a PhD student, when I wanted to decode hidden worlds in our own homes and see through walls. This kind of research has had a lot of real-world impact. It's already being used in medical studies at major hospitals. Doctors are using our technologies to monitor disease progression in patients with Parkinson's, Alzheimer's, and COVID-19. All of these diseases are associated with changes in mobility, which are imperceptible otherwise, but which we're able to sense them using wireless technologies. This technology has been commercialized. It's been deployed in hundreds of homes already. And a few years ago, we were invited to the White House and we demoed it to President Obama. We also visited the UK and demoed it in the UK House of Lords. But probably the biggest highlight is the one that Cecilia mentioned in the beginning of this talk, which is that the Big Bang Theory made fun of us. They made an entire episode, if you want to go and watch it, that's episode 14 of season 10, about this technology where they made fun of MIT scientists that want to recognize human emotions, which is yet another thing that this technology can enable. All of this work would not have been possible without the many talented researchers that I work with. You can see them here in the photo earlier in the academic year before COVID hit. And along with our collaborators, we think about hidden worlds that we would love to explore. We try to work to decode these hidden worlds through scientific exploration with the ultimate goal of contributing to societal problems. And I would like to wrap up my talk by saying that this research is very exciting for me personally, because on one hand, it involves deep technical challenges and it makes connections between multiple fields. And on the other hand, these technologies enable many powerful applications, ranging from helping us understand and address humanity's existential crisis, climate change, through our ocean technologies, to building new tools for monitoring and treating new diseases like Alzheimer's, Parkinson's, and even cancer. And because it also paves way for future applications in space exploration. And with this, I want to wrap up my talk. Thank you very much for listening, and I'm happy to take any questions.